Okay, it's the physics video lecture once again. Physics 107B video lecture 5. Today we're talking about Maxwell's equations once again, without all the boundary conditions and the relations in matter, but just the basic Maxwell equations and conservation laws. So let's just call this Maxwell equations and conservation laws. And we'll just write them all down and draw some conclusions. So let's see what we have here. So first of all, we'll just write down divergence of E equals rho over epsilon naught and work our way through. Second law, divergence of the magnetic field vanishes, and we have Faraday's equation, E, other way around, curl of E, curl of E equals dB dt minus, and then the Ampere Maxwell curl of magnetic field. We've got the current density plus the new displacement current, E dt. And if we want to round those out, we also need the force law plus the force law. So this is the force on a charged particle, E plus V cross B. So these equations should summarize all of classical electricity and magnetism, because the properties in matter, added to this, but these were the fundamental quantities, and you just had material properties that modified the strength of these. So, and same, we needed boundary conditions, but we don't have to deal with these today. So they summarize electricity and magnetism, and so summarize electricity and magnetism. The idea is supposed to be able to get everything out of these equations now that you've found them. So, first example, I'll just remind us. We take a point charge. Take a point charge, so we have density equals Q delta of R. So there's our point charge. Then we would have this law right there, divergence of E would be equal to Q over epsilon naught delta of R. And we know the property of a delta function. We're going to integrate both sides over a volume. Integral divergence of E d volume equals integral over that's just going to give us a 1, so it gives us Q over epsilon naught, which is our point charge, right? So this is at the origin, point charge at the origin. And now we use, and this was over a volume, so we use the divergence theorem over the boundary of a volume to have E dot n hat d area equals Q over epsilon naught. And then you remember how this goes. We're going to say not just any old volume, but a sphere of radius r centered on the origin. And then our symmetry argument tells us that E just has to be a radial force. And we end up with E times 4 pi r squared over here, Q over epsilon naught. And when I want to go to the vector, I said it had to be a radial force to make this argument, and I have the Q over 4 pi epsilon naught r squared, r hat, that's Coulomb's law. Okay. So we get Coulomb's law out of this, clearly. So the next thing we could do is look at Ampere Maxwell. So next, take the divergence of equation 4, divergence of equation 4. And we have identically divergence of curl equals 0. So we have 0 equals mu naught divergence of J plus mu naught epsilon naught divergence of dE dt, and we can cancel the mu naught. We've got the divergence of J. We've got epsilon naught. Then we have dE dt, or we'll pull out the time derivative, and we'll have the divergence of E is rho over epsilon naught. So that time derivative is d rho dt, 1 over epsilon naught. And those cancel, and we have the continuity equation. So we have d rho dt. Of course, yeah, we built it in the opposite direction, so of course we obtained it again, but here we go. Divergence of rho equals 0. And we know that expresses conservation of charge. So here we had Coulomb's law. Here we have conservation of charge that comes right out. Charge, Coulomb. Okay, so what about the other conservation laws? This is the new conservation law we learned about with electricity and magnetism. Back in classical mechanics, we had conservation of energy, we had conservation of linear momentum, conservation of angular momentum. So the next question is, what about the other conservation laws? Four. What about other major conservation laws? Question mark. And this is going to get interesting. There's more going on in electricity and magnetism. Before I erase this board, so we have these field equations, and we have the force on a charged particle. So we still have just the mechanical energy of an assemblage of charged particles. Okay, they can be moving around. They have attractive and repulsive forces that takes work to assemble them into some configuration. But then we're going to see that there are energies associated with the fields as well. Okay, and between the two of those different types of energies, there's clearly more going on. And yeah, we're going to, of course, use these equations, but I'm going to erase them now. Good. So we'll start with the energy in the electromagnetic field. numbering these things, for which we already have expressions. We had the square of the magnetic and the square of the electric fields giving us an energy density. So I'll write that down as the electromagnetic energy. We have epsilon naught field squared plus 1 over mu naught B squared was a half both of these d tau, so that's energy per volume times volume, and that's going to be our electromagnetic energy density. Okay. Next, we're going to talk about the work done on an assemblage of charges. So work done on charges by the fields. Okay. So we'll start with a single charge. So you have dW and this is the mechanical work done on the charges by the field. So you've got the Q or your F dot dl, and then we'll just plug in what we had just erased. So we have Q E plus V cross B dotted into dl, and because there's motion involved, we have the dl can be a vdt. So Q E plus V cross B dotted into V dt. So for this reason, the V is going to be, the dot product of V and V cross B vanishes. Okay, and so we just end up with the Q E dot V dt. But now we're going to express that in terms of J. Sure. Good. That's good as far as it goes. So now we integrate. So we're just summing over all of these. And the individual charge, similar to what we did with the delta function, but the individual charge is just rho d volume. Okay, so there's our individual charge, and then we have E dotted into this V, but we can call that J divided by rho. And these are going to cancel. Okay, I don't have to write that. They're going to cancel, and so we have E dot J d tau. So that is the energy, and this is going to be over some volume, but write it or not. That's the energy. Next, we're going to turn this, we're going to express this J via the Ampere Maxwell equation in terms of the fields. Okay. So next, express J in terms of the field. E and B. So now we just need the expression for E dot J. J we get out of the Ampere Maxwell equation, and then there are a couple of product rules involved. So here we go, E dot J, E dot J, Ampere Maxwell, I'll just write this down. E dot, so we just solve for J, so we've got 1 over mu naught curl of B minus epsilon naught d E dt. And I can write this as 1 over mu naught E dot curl B minus epsilon naught E dot dE dt. So there are a couple of things we can do with this. There is a product rule that we're going to invoke right here. So in fact, I'll write directly under here for this product rule. We have E dot curl of B equals B dot curl of E minus divergence of E cross B. Oops. E cross B. And then you'll notice this E times dE dt, it's all numbers these. 1, 2, we've got the E dot dE dt will be 1/2 time derivative E squared, or the vector E dotted into itself. We're going to have the same thing for B. I'll just write same for B, which is going to come in there via via curl of E dB dt. Yeah. Curl of E minus dB dt. So yeah, that's just a law of differentiation. That's one of the Maxwell equations. That's just a product rule from the long list of product rules that we have. So we put all those ingredients together, and let's see what we get here. We get for E dot J equals let's skip a couple lines because actually they're all right here. You make those substitutions. You have minus 1 over 2 mu naught with your d dt b squared, same thing, minus epsilon naught over 2 d dt e squared, and then this cross divergence of this cross product. So minus 1 over mu naught divergence E cross B. So yeah, those ingredients, this is just a product rule. You can see where we substituted this with B dot curl of E and this one, okay? So this one ended up here. This one here ended up right here. And this, with the curl of E, turned into 1 over 2 mu d over dt b squared because we plugged in Faraday's law. Okay. So what we do now is remind ourselves, well, we had an integral here. So that was this integral, so we're right directly underneath it. And we can now write for this energy. Oh, good thing I caught that. E dot J, I divided by dt, so this was actually a power. Okay, this is a power J, E dot J d tau, so I had divided by the dt. Important. Yes. Okay, good. So now we have d w dt. That's the power, and we'll just take them one at a time. We've got the minus sign, so we can actually pull the minus sign out, integral 1 over 2 mu naught. In fact, we can pull out the time derivative already. So minus 1, make sure I did that way. Yeah. Well, we'll do it in 2 steps. So good, we'll leave this inside for the moment because we have to do a couple things here. So yeah, just copying this d tau, we have minus 1, 2 mu naught, dB squared dt, minus epsilon naught over 2, dE squared dt. There's a d tau. And also a minus integral divergence E cross B d tau over mu naught. So yeah, here we're integrating over volumes. Yeah, the next step, I'm just going to pull out the time derivative. Got enough room here, I'll write it a little smaller. Okay, pull out the time derivative and the minus sign. And then what we're left with is just that energy density integrated over volume. So there's the 1 over 2 mu naught, d squared plus epsilon naught, d squared over 2 d tau. Here we're going to invoke Gauss's theorem again because we have a divergence, so we can say minus E cross B over mu naught dot n hat d area. The area, this is the volume. This is the surface that bounds the volume. Okay. So here we can already see what's going on. We have a change in energy inside this volume, energy of the B field, of the electromagnetic fields. And here we have a flux, so energy leaving that volume, right? Both of them have a minus sign in front of them. Now the total energy we've been talking about is not yet up here because this work that we originally constructed here was for the mechanical energy of those charges being pushed around, as seen by, let's back aboard. Okay. So this is actually the change of the mechanical work with respect to time. So we're going to put all three of those together. This we recognize as the electromagnetic energy density. Here, there's a flux. So here, I'll put a star here. So note that W dt was the change of the mechanical energy. And this is whatever's going on in that volume. So now what we have is, and I can do the whole thing at once on this. So now we have d dt integral over the volume. All right, U mechanical, so that would be the mechanical energy density plus U electromagnetic. That is this one. And then yeah, I'm going to even add, I'm going to add this one as, again, divergence of E cross B divided by mu naught. Okay. D volume. Okay. Equals 0. So I just brought those both over to the other side. And this is Poynting's theorem. Yeah, this is, yeah, I can define things right here. So this is called the Poynting vector. Yeah, so I've got vector S is equal to 1 over mu naught E cross B and I'm going to go ahead and take these time derivatives back inside as partials, and calling this an arbitrary volume standard argument, the integrand will then vanish. Okay. And the integrand will have the form of the following. So coming out of here, we have d dt U mechanical plus U electromagnetic plus the divergence of this Poynting vector S is equal to 0. That's Poynting's theorem. Yeah, so up here, we saw this as a flux. Okay, so there's a flux through the surface of the volume. So it's really the same as another continuity equation. This is a continuity equation for energy. Okay, so what are the units of this vector S? Okay, you had S d area, so it's really a power and intensity. E cross B is a power times dA will give you, yeah, E cross B times dA will give you power. So it's power per area and intensity. What else is to say about this? Yeah, I didn't really specify the difference between the mechanical and the electromagnetic. So the electromagnetic is this integration of these B and E squared B and E fields. The mechanical contribution is really the work it takes just to bring some charges with attractive or repulsive forces into some configuration with respect to each other, because that work is not the same as these squared fields. Okay, so that would be the mechanical contribution. Electromagnetic contribution, again, this expression right here, and the change of those locally, or you can integrate it over a volume and talk about the flux, but the change of these locally is just another continuity equation. So instead of conservation of charge, we have here a conservation of energy. Okay? It's a conservation of energy, and it's mechanical and electromagnetic. So this is conservation of energy. Again, locally, and if you have it integrated over some volume, you'd say the energy inside that volume is increasing or decreasing, as the flux here, this pointing vector flux, leaves or enters that volume. Okay, excellent. I'm going to consult the clock here. Okay, we're just going to wrap it up today with, now that we have this conservation of energy, we'll discuss linear and angular momentum. Although we're not going to solve it yet, we're just going to discuss it on a principle level. So what do we have now? We have charge and energy, and we see the form of the conservation law pretty nicely. The charge has the same form as the energy with the continuity equation. And on the other hand, you can translate both of them to the behavior in a volume and what's flowing in or out of that volume. Okay, so that's pretty satisfying. What we'll look at now is the discussion of the linear and angular momentum. We had seen earlier that there was this mystery of the angular momentum in the field with that rotating wheel and Faraday's law. So we're aware of that. We're not going to solve it yet. Namely, the form of the linear and angular momentum will not yet be solved, but we'll just bring it to our attention again. So here, let's write, what about linear and angular momentum? What about linear and angular momentum? Question mark. Well, we're looking at an assemblage of charges. So they have linear and angular momentum just flying around in space. So if we're looking at classical mechanics, and our force law presupposes classical mechanics. So when we were talking about F equals Q E plus V cross B, that's exactly what we're talking about. So we're on that same ground. So let's remind ourselves, m sub I times acceleration is equal to F sub I. We have the external forces and then internal forces, let's say Fij, summing over J. Fii identically 0 out there. So for the conservation laws, we could do two things. One thing is we could just add these. So we had sum over I, mi/i, second derivative, sum over external forces, and then the sum over all the internal forces. So that was I and j Fij. And what we did was we assumed Newton's third law. And then every pair of forces here would cancel. Because for every ij, you'd have a ji, and they'd be equal and opposite by Newton's third law. And that made this whole sum go away. And then what you were left with was d dt sum over mi/ri dot. So this was, of course, the total linear momentum of the system, and that was equal to the sum of these is just the net external force. And then you would say, well, if the net external force vanishes, then we have conservation of linear momentum. And the net external force vanishes if you just have the forces of the particles acting on each other. This external force was always some external field. So that's how you got conservation of linear momentum. And the question is, how is that going to be with electricity and magnetism? The other, so yeah, anyway, the upshot of this was total linear momentum is conserved if no external force, if no net external force. Yeah, and the argument again, Newton's third law has to hold. Now we have something similar with the angular momentum, and I'll just remind you of that argument as well. So the other possibility here, or the other thing we had to do, call this 3, was to multiply this equation, cross multiply from the left by r and then sum. So I'll do both of those steps at once. So then we could also have sum over r sub I cross m sub I ri acceleration equals sum over r sub I cross f sub I external plus, and that was over I, plus this double sum, same as before, I and j, r sub I cross f sub I j. Okay, so what happened here? So again, actually, what I'll do is this time I'll save. So we end up with complete time derivative of r sub I cross m sub I r sub I. First derivative. So this turns into the total angular momentum. L total. And this here turns into the torque. I'll use the letter T, net external. This turns into the torque, and so this has to vanish, because then you say if I have net external torque equals 0, then my total angular momentum is conserved, right? Same argument, but we have to bring this to vanish, and the way we do that is we got I and j, we have r. I'll just rewrite this. R sub I cross Fij. What we have with those pairs there is R sub I cross, no. Fij minus Fji. Fij plus Fji. Actually, let's see if I'm missing something here. Once more, we feel it. Our pairs go this way. R sub I minus R sub j cross Fij. Okay. Because when you switch the indices here, you're switching the index on one of these. Okay. So here you need the equal and opposite we had up here. Okay. But you need more than equal and opposite. In order to bring a pair like this to vanish, you need it to be a central force. So here we have Fij equals minus Fji and central force, because if there's central forces, then these forces will be parallel to R sub I minus R sub j, and then the cross product of parallel vectors vanishes. And central force. So that's what's required in mechanics, just using Newton's laws, to have conservation of angular momentum. So then if tau external vanishes, these vanish because they're central forces, Newton's third law, then you have total angular momentum conserved. So, all right, L total equals constant if, first of all, if no external torque, and this right here, okay, Newton's third law and central forces. So the question is that the case in electricity and magnetism? Newton's third law and central forces. So there's a good little sketch in the text, and I'm just going to explicate that, because you see very clearly that the answer to these questions is no. So how are we going to title this? So I'll just call this Newton's law in electrodynamics. Newton's law, or E&M. So here's what we do. We just sketch it. We make this one pretty big. We've got X, Y, and Z axes, and the idea is we have two particles, charged particles, let's say they both have positive charge, and they're both headed for the origin. So this is V1, this is V2, Q1, Q2, and there are going to be forces here. Do I have it down anymore? The electric force we can think of as being radial. Okay, so that's opposing each other, but there's also the magnetic force. And the magnetic force is so due to this charge here, Q1, think of the B, yeah, how about just if we have charged particle going in this direction? Just think of it as in your right-hand rule. Okay. In fact, easiest to think about if we had a particle going in this direction, then we would get those circular fields. Right-hand rule, you know, thumb is the current or the velocity vector, and the direction is your fingers. So if you do that for these, then this particle coming towards here is going to give you one into the into the board, and this one coming down here is going to give you out of the board, and the forces, the magnetic force on this particle will be in this direction. All things being equal, this one will be in that direction. Okay. So you are not having this condition satisfied at all. These forces are not just anti-parallel. Because this was electric, this is magnetic, this is electric, this is magnetic. Okay, so what can we conclude? So here, Newton's third law does not hold. Okay. In other words, the forces are not equal and opposite. And therefore, we can't assume these conservation laws. So what's going to happen, in other words, if these were gravitating particles in some kind of orbiting configuration, those conservation laws would hold. Okay. Here we can imagine some charged particles in some kind of orbiting configuration as well. The conservation laws do not hold, and what we're going to find is that it's going to be the electromagnetic radiation, or first of all, it's just going to be the fields that not only have energy but also linear momentum and angular momentum. And in fact, when we talk about waves, the fields are going to carry some of that linear and angular momentum away, away from the system out to infinity. So that's going to be a really interesting resolution to everything. And it's all going to follow out of Maxwell's equations. And of course, we had to use Newton's law here, but in terms of those other quantities, it's going to all be Maxwell. Okay, good. See you guys next time.